College Trigonometry, Chapter 10, Section 4, the trigonometric or polar form of complex numbers. Now, when we think about complex numbers, remember these are the numbers that involve I. They're in the form a plus bi. You can't order them on a number line like you can real numbers. One way to organize and to picture them is by using a graph. And in order to graph a complex number, what we do is we take our existing coordinate system, the xy axis, but instead of an xy axis, we have a real axis in place of the x and an imaginary axis in place of the y axis. And it looks something like this. To graph a complex number like 2 minus 3i, we draw a vector from the origin and to the point 2, negative 3, 2 on the real axis and negative 3 on the imaginary axis. Note that a plus bi is called the rectangular or standard form of the complex number. Now we can add two complex numbers. We've done that before. Remember, you just add the real parts, add the imaginary parts. You can also do this using the vector, just like we talked about. You're going to add the two vectors together. This should look very familiar. We just did this in the last section. The resultant of the sum of the vectors corresponding to the two numbers is illustrated below. So you can see there the resultant vector from adding 1 plus 3i to 4 plus 1i. Find the sum of 6 minus 2i and negative 4 minus 3i. Graph both complex numbers and the resultant. Pause the recording, give it a try, and resume to check your answer. Well, we've added these before. This should be no big deal. It's 2 minus 5i. Graphically, we're going to graph negative 4 minus 3i and 6 minus 2i. Draw the rectangle, and the diagonal is the resultant vector of 2 minus 5i. Now, if we put the complex numbers into trigonometric form, it's a little easier to divide, multiply, and to find roots. Note the relationships between the complex number x plus yi and the triangle formed from the vector. This should look really familiar. We've done this probably 100 times by now. The relationship between the different parts of the triangle there, x is r cosine theta, y is r sine theta. Again, should be very familiar. How do we find r? Well, we use the Pythagorean theorem. R is the square root of x squared plus y squared, and the tangent of theta is y over x. So we've seen these relationships before. Now, if we substitute x equals r cosine theta and y equals r sine theta into x plus yi, then we get, instead of x plus yi, we get r cosine theta plus r sine theta I, which is, if you factor out the r, it's r times the quantity of cosine theta plus I sine theta. This expression is called the trigonometric form or the polar form of the complex number x plus yi. So r times the quantity cosine theta plus I sine theta. Now, there's another way to write this a little bit shorter. Instead of writing that out all the time, it can be written as r cis cosine I sine theta. So it's just a little shorthand notation. The number r is called the modulus, or the absolute value of the complex number. The angle is called the argument of the complex number. Okay, now let's try this problem. You're going to express 2 times the cosine of 300 degrees plus I sine 300 degrees in rectangular form. Very simply, you're just going to put in the cosine of 300, the sine of 300, and distribute. These are reference angles. These have special angles as reference angles, so you need to use exact value for these, please. Pause the recording, give it a try, and resume to check your answer. Okay, and the cosine of 300 is 1/2. The sine of 300 is negative square root of 3 over 2, so we substitute those in. We multiply through by the 2, and you get 1 minus I square root of 3. Now, notice we can do this on our calculator. However, it's going to give you an approximation, and you need to make sure that you can write this in exact form. So to convert from rectangular to trigonometric form, what you're going to do is you're going to sketch a graph of the number in the complex plane. You're going to find r, and then you're going to find theta by using the equation tangent of theta equals y over x. And then choose the quadrant that is indicated from the sketch. So the sketch helps you figure out what quadrant this thing is going to be in. Write each complex number in trigonometric form. Pause the recording, give this a try, and resume to check your answer. Okay, for A, we have the x is -3 and y is 1. Made a sketch of it. It's in quadrant 2. R is found using the Pythagorean theorem. So we get 2. That 2 should not be under the square root there. Okay. Now we're going to find theta by doing y over x. Y was 1, x is negative square root of 3. So we have negative square root of 3 over 3. Well, the angle that has a tangent of negative square root of 3 over 3 is pi over 6. And moving that into the appropriate quadrant gives us 5 pi over 6. So in polar form, negative square root of 3 plus I is 2 times the cosine of 5 pi over 6 plus I sine of 5 pi over 6, or 2 says 5 pi over 6. And then for part B, x is 0, y is -3. So we get r is 3, and tangent is undefined. So if tangent's undefined, we need to find another way to do it. Well, if you sketch the graph of it, which you were supposed to do anyway, you see that it goes, you see where it is there. It's 270 degrees, or in terms of radians, 3 pi over 2. Now, I noticed in the first problem they were going to radians. Here they're going to degrees. So watch out for that. I'm not sure why they're switching back and forth without warning you. But be aware, follow the directions on your homework or directions on whatever you're doing to make sure you're in the right mode. But you should know that 270 degrees, that's where we have an undefined tangent. That's going to be our theta. So 3 says 270. This is an application problem. First of all, what in the world are we talking about, the Julia set? Well, high resolution in computer graphics and complex numbers make it possible to produce shapes that are called fractals. Now, you can sketch fractals, but to truly draw a fractal, you do need computer graphics. The term was first used by Mandelbrot in 1975. A fractal is a geometric figure with an endless self-similarity property. What that means is that it endlessly repeats itself. No matter how much you magnify any part of it, you zero in on one part and you magnify it, you see a repetition of the pattern you saw in the larger part, and it's endlessly magnifiable, which is why to really truly do it, you need a computer. So we have this fractal called the Julia set. It's shown in the figure. To determine if a complex number is in the set, you perform the following sequence. You repeatedly compute the values of z squared minus 1. So z squared minus 1, you got z squared minus 1 squared minus 1. Take that, square it, minus 1. Take that, square it, minus 1. If the moduli of any of the resulting complex numbers exceeds 2, then z is not in the Julia set. And you'll notice a pattern. That's what you're looking for. Otherwise, z is part of the set, and the point should be shaded in the graph. So we're going to determine if 0 plus 0i belongs in the Julia set. Now, if you want to give this a try, following the directions there, go ahead and pause. If not, then keep going, and we'll look at the answer. Okay, so z equals 0 plus 0i, which is 0. So z squared minus 1 would be 0 squared minus 1, which is negative 1. Square that and subtract 1, you get 0. Square that, subtract 1, you get negative 1. Square that, subtract 1, you're going to get 0. So it's going to go back and forth between 0 and negative 1. It's either going to be 1 or the other. So it does belong to the set. It does not exceed 2. In fact, it doesn't exceed negative 1 or 0. Products. Multiplying complex numbers. Now, we've done this before. If you have to multiply complex numbers, you do have to FOIL it out. You have to remember that I squared is negative 1, and you see there the process. Now, in trigonometric form, here's the whole process. And it looks really super complicated. However, we're going to show you a shortcut to that, but this is the process. Multiplying the same thing out, we get a cosine 210 plus I sine 210. By the way, if you're looking through the process, what we did to go from, let's see, about step 3 to 4 there, where I've got the arrow, is that we used the sum and difference formulas for sine and cosine in order to simplify that. Here's our product theorem. All of that to say that if you are multiplying these two complex numbers like that, then what you get in compact form is you have R1 cis theta 1, R2 cis theta 2, plus R1 times R2 cis theta 1 plus theta 2. So that's a little formula for multiplying the complex numbers. So try this out for yourself. Find the product of 3 cosine 45 plus I sine 45 and 2 cosine 135 plus I sine 135. Okay, putting everything in the formula, we have 3 times 2 plus times cosine 45 plus 135 plus I sine 45 plus 135 gives us 6 cosine 180 plus I sine 180, and then substituting the values in, we get 6 times negative 1 plus I times 0. Now, when you're trying to do a quotient, it can be really messy too for complex numbers. So you see the whole process here. We have to rationalize the denominator and all of that just to get negative 1/2 I. In polar form, what we can do to do the two complex numbers is, notice what we have here. We've switched in both to polar form, and then they actually switch the answer to polar form and see if there's a relationship between them. What you may notice is that if you subtract 60 minus 150, you get negative 90, and if you divide 2 divided by 4, you get 1/2. So there's the pattern. If you're dividing, basically what you're going to do is R1 cis theta 1 divided by R2 cis theta 2. And then it gives you a little different form, R1 over R2 cis theta 1 minus theta 2. All right, so try to find the quotient here and write the result in rectangular form. Pause the recording, give this a try, and resume to check your answer. It's actually pretty easy to use the formula. It's going to be 10 over 5 cis of negative 60 minus 150. And that gives you negative 210. And so you've got the polar form right there. To do the rectangular form, you need to actually take the cosine of negative 210 and the sine of 210 and go ahead and distribute the two. The question may become, which is easier? Is it easier to convert it to polar form and then divide? Or is it easier to leave it as complex form and divide? Polar form looks a little easier, at least on this problem. All right, the rest of this recording is additional practice, so if you will pause the recording, give these a try, and resume to check your answer, and continue that way through the rest of the recording.